In early December 2024, Google's quantum computing division published a blog post announcing a new chip called Willow. Buried in that post, past the technical specifications and the benchmark numbers, was a single sentence from Hartmut Neven, the physicist who founded and still leads Google Quantum AI, that did something almost no corporate announcement ever manages to do. It dragged a 100-year-old argument about the nature of reality itself back into the headlines. Neven wrote that Willow's performance was so phenomenally fast, it had to have borrowed its computation from parallel universes. Not as a metaphor, not as marketing flourish, at least not entirely. As a genuine argument from a physicist that his chip's speed was evidence the multiverse is real. Within days, that single sentence had eclipsed almost every other detail of the announcement, spreading across tech press and science media alike under headlines asking whether Google had just proven parallel universes exist. Physicists spent the following weeks arguing about whether Neven had just offered a legitimate scientific claim, or badly overstated what his own hardware had actually shown, weighing in through blog posts, op-eds, podcast interviews, and eventually peer-reviewed commentary, an unusually fast and unusually public cycle for a disagreement rooted in decades-old interpretive physics. That argument, unusually, played out almost entirely in public, on the record, with named scientists on both sides, and it's still not fully settled. This is the story of what Willow actually did, why one of the field's own leaders reached for the multiverse to explain it, why most of the physics community pushed back hard without ever denying that the underlying engineering achievement was real, and what actually happened in the year that followed, once the noise around parallel universes finally died down. Start with what a quantum computer actually is, because the claims on top of it only make sense once the foundation is clear. An ordinary computer, the one in your phone or laptop, stores information as bits, each one strictly a 0 or a 1. A quantum computer stores information in qubits, and thanks to a genuinely strange property of quantum mechanics called a superposition, a qubit can exist in a combination of 0 and 1 simultaneously, not as a trick of description, but as a measurable physical fact, until the moment you measure it and force it to settle into one state or the other. Link enough qubits together through another quantum property called entanglement, itself one of the most thoroughly tested and experimentally verified phenomena in all of physics, and the number of simultaneous states the system can represent grows exponentially with each additional qubit. That's the entire promise of quantum computing in one sentence. Certain classes of problems that would take a classical computer longer than the universe has existed to brute force could, in principle, be solved by a quantum machine exploiting that exponential space in a reasonable amount of time. The catch for essentially the entire history of the field since quantum computing was first theorized in the early 1980s has been that qubits are extraordinarily fragile. The faintest vibration, stray photon, or temperature fluctuation can collapse their delicate quantum state, introducing errors, and historically, the more qubits you add to a chip trying to do something useful, the more errors accumulate, faster than you can correct them. That problem, known as the error correction threshold, is the single biggest obstacle standing between today's quantum chips and a genuinely useful, the general-purpose quantum computer. And it's the specific problem Willow was built to attack. Willow wasn't Google's first attempt at a headline-grabbing quantum milestone, and the earlier one is worth knowing, because it set both the scientific stakes and the public skepticism that Willow later walked into. In 2019, Google's earlier chip, Sycamore, became the center of the field's first major quantum supremacy claim, a term coined years earlier by Caltech physicist John Preskill to describe the moment a quantum computer performs a calculation no classical computer could complete in any practical amount of time. Google reported that Sycamore had done exactly that, completing a benchmark calculation in about 200 seconds that the company estimated would take the world's most powerful classical supercomputer roughly 10,000 years to replicate. IBM, a competitor running its own large-scale classical simulations on its Summit supercomputer, pushed back within days, arguing that a sufficiently optimized classical supercomputer could actually complete the same task in a matter of days rather than millennia, not minutes, but nowhere near 10,000 years either, and that Google's estimate had understated how cleverly a classical machine could be programmed to attack the specific problem. That dispute was never fully resolved to everyone's satisfaction, and it left a lingering skepticism in the field toward headline quantum advantage numbers generated and verified largely by the company making the claim. A skepticism that shaped how carefully outside researchers scrutinized every subsequent Google announcement, Willow included. Willow's 2024 announcement inherited that skepticism directly, and it's part of why outside physicists were quick to scrutinize both the 10 septillion-year figure and, especially, the multiverse interpretation Neven layered on top of it. Google's own announcement described two separate achievements, and it's worth keeping them distinct throughout everything that follows, because only one of them is where the multiverse claim actually comes from. And conflating the two is exactly how the more overstated headlines ended up happening in the first place. The first achievement was a milestone in error correction. Google reported that as it scaled Willow up, using progressively larger grids of physical qubits to encode a single, more stable, logical qubit, the error rate dropped exponentially instead of climbing, a result the field calls operating below threshold. The specific method Google used is called a surface code, a way of arranging physical qubits into a two-dimensional grid where neighboring qubits constantly check each other for signs of error without directly measuring, and thus destroying, the fragile quantum information they're protecting. As Willow's grids grew from a 3x3 arrangement of qubits to 5x5 to 7x7, the logical error rate per cycle roughly halved at each step rather than climbing, exactly the trend theorists had predicted would eventually be possible, but nobody had cleanly demonstrated in physical hardware. Researchers had been chasing that specific milestone for nearly 3 decades, because it's the mathematical condition that has to hold true before quantum error correction can actually make a large-scale, fault-tolerant quantum computer feasible at all, rather than an engineering dead end where every added qubit just adds more noise than it's worth. Independent of any speed benchmark, that below-threshold result is a genuine, widely acknowledged, peer-reviewed technical accomplishment published in the journal Nature, and it's the part of the Willow announcement that drew the least controversy, because it's a straightforward engineering claim that other labs can, in principle, replicate and check. The second achievement is the one that produced the Multiverse headline, and it's a benchmark called random circuit sampling, or RCS. The task itself is deliberately, almost artificially, hard for a classical computer, and largely useless outside of demonstrating raw computational power. You run a specific, complicated sequence of quantum gate operations across the chip's qubits and sample the resulting probability distribution of outputs, repeating the process many times to build up a statistical picture of which output patterns the chip actually produces. Simulating that exact distribution on a classical supercomputer requires effectively tracking every possible quantum state the system could be in as the gates are applied, a computation whose memory and processing requirements explode exponentially as you add qubits. Since each additional qubit doubles the number of possible states the simulation has to keep track of simultaneously. Google reported that Willow completed a standard RCS benchmark in under 5 minutes, a task the company estimated would take one of today's fastest classical supercomputers roughly 10 septillion years, a one followed by 25 zeros, a number that, as Neven put it in the announcement, vastly exceeds the age of the universe. It was that specific, almost absurdly large number that Neven used to justify the multiverse claim, reasoning that a calculation that fast, exploring that vast a computational space, made more intuitive sense if you imagined the actual work being distributed across countless parallel realities rather than confined to the one classical universe we can observe. To understand why Neven's argument wasn't pure invention, you have to know that he wasn't the first physicist to connect quantum computing to the multiverse. That link goes back decades, to physicist David Deutsch, one of the founding theorists of quantum computation itself, who argued in the 1980s and 1990s that quantum computers only make intuitive sense within the many worlds interpretation of quantum mechanics. The idea, first proposed by physicist Hugh Everett in 1957 as his doctoral thesis at Princeton, that every quantum measurement doesn't collapse into one random outcome, but instead splits reality into multiple branches, one for each possible outcome, all of which go on existing, just unable to interact with each other afterward. Everett's original proposal was largely ignored for over a decade after he published it, in part because Niels Bohr's Copenhagen interpretation already dominated the field, and in part because Everett left academic physics for a defense industry career shortly after finishing his degree. The many worlds interpretation only gained serious traction in physics circles starting in the 1970s, championed by physicists like Bryce DeWitt, and it remains, to this day, a genuinely contested but seriously held position, regularly defended in academic journals and university physics departments, rather than confined to popular science writing. Under many worlds, Deutsch argued, a quantum computer's advantage over a classical one comes from performing pieces of the calculation across those parallel branches simultaneously, and then interfering the results back together at the end when you take a measurement, an idea he laid out formally in a landmark 1985 paper that's still cited today in debates exactly like the one Willow triggered. It's a real, serious, still debated interpretation of quantum mechanics, taught in physics departments and defended by working physicists, not a fringe theory invented for a press release. Neven's blog post was explicitly invoking that same Deutsch-style reasoning, dressed up for a general audience and attached to a specific headline-friendly number. And that's exactly where most of the physics community drew the line, not on whether many worlds is a legitimate interpretation, but on whether Willow's benchmark result actually constitutes evidence for it. The pushback was immediate, public, and came from working physicists rather than internet skeptics. Science writer and astrophysicist Ethan Siegel published one of the most widely cited rebuttals. arguing flatly that quantum computation does not occur in many parallel universes, does not occur in any parallel universes, and does not demonstrate or even hint that we live in a multiverse. His argument, echoed by numerous other physicists in the following weeks, was that Neven had confused a mathematical description with a physical claim. Quantum mechanics does describe superposition using something called Hilbert space, a purely mathematical framework where a system's possible states are represented as vectors that can combine and interfere. That framework works identically, producing identical testable predictions, whether you interpret it through many worlds or through the older, more conventional Copenhagen interpretation, associated with physicists Niels Bohr and Werner Heisenberg in the 1920s, where a quantum system genuinely exists in an indeterminate state until measurement collapses it into one single non-branching outcome, with no other branches ever existing anywhere, or through several other competing interpretations, including pilot wave theory, developed by Louis de Broglie and later David Bohm, which keeps a single classical reality but adds a hidden guiding wave that determines a particle's path in advance, deterministically, without ever branching at all. Every one of those interpretations makes the exact same experimental predictions for something like random circuit sampling, down to the last decimal place, which is precisely why physicists have argued about which one is correct for the better part of a century without any experiment settling it. That's the core of the physicist's objection. Willow's speed is real, and it genuinely demonstrates that quantum computers can outperform classical ones on specifically chosen problems. But the benchmark cannot, even in principle, distinguish between competing interpretations of what's actually happening underneath the math, because all of those interpretations were built from the start to agree on the predictions and disagree only on the philosophical picture behind them. A calculation running fast doesn't tell you which philosophical picture is correct, any more than a calculator solving a differential equation quickly tells you whether numbers really exist as Platonic objects. There was a second, more practical objection running alongside the philosophical one, and it's worth being just as direct about it. Random circuit sampling was chosen, deliberately, because it's close to the hardest possible task for a classical computer relative to how easy it is for a quantum one, which makes for a dramatic benchmark number, but it isn't a useful calculation in any applied sense, and Google has never claimed otherwise. Google itself has acknowledged in the same announcement and in follow-up interviews that RCS has no known real-world application on its own. It exists specifically to demonstrate the presence of a computational gap between quantum and classical hardware, not to solve a problem anyone actually needs solved. Critics also noted that the benchmark and its classical runtime estimate were both defined and calculated by Google itself, using its own assumptions about the best available classical algorithms and hardware, which doesn't invalidate the result, but does mean independent groups needed time to check the comparison rather than take the 10 septillion year figure at face value, echoing exactly the kind of scrutiny IBM had applied to the 2019 Sycamore claim. None of that undercuts the below threshold error correction milestone, which stands on its own regardless of how you interpret RCS. But it does mean the specific number that anchored the multiverse claim, headline-grabbing as it was measuring engineering speed on an intentionally exotic problem, not evidence about the fundamental structure of reality. It's worth fast-forwarding to see what Google did next because the field didn't stop at Willow's initial debut, and the follow-up matters for understanding how seriously to take the original hype. Throughout 2025, Google kept refining Willow, and on October 22nd, 2025, the team published a new result in Nature that addressed the practicality criticism head-on, using an algorithm they called quantum echoes, built around measuring something physicists call an out-of-time order correlator, essentially a way of tracking how a small disturbance spreads and scrambles through a complex quantum system over time. Google reported the first verifiable quantum advantage, a calculation that ran roughly 13,000 times faster than the same task on the Frontier supercomputer, one of the fastest classical machines in the world. But unlike random circuit sampling, one whose specific numerical output could be independently checked by running the same experiment on a separate quantum device, rather than only by an expensive classical simulation. The technique works something like sonar. The algorithm sends a signal forward through a network of 65 entangled qubits, perturbs a single one of them partway through, then effectively runs the process backward in time to listen for how that tiny disturbance echoed through the rest of the system. Because the resulting measurement is a physical expectation value, the kind of number you could, in principle, also measure through an entirely different experimental technique like nuclear magnetic resonance, rather than an abstract bit string only checkable by simulating the whole quantum circuit classically. It sidesteps the verification problem that made critics uneasy about random circuit sampling in the first place. Working with researchers at UC Berkeley, the team used quantum echoes to help predict the molecular structure of two chemical compounds, then confirmed those predictions against real nuclear magnetic resonance spectroscopy measurements in the lab. a genuinely useful application in chemistry rather than an abstract stress test. Google's own quantum chemist on the project, Nicholas Rubin, described the goal explicitly as augmenting techniques scientists already use to study molecular structure, connecting the benchmark directly to a real scientific workflow for the first time. That October 2025 result drew far less controversy than the original Willow announcement, largely because nobody attached a multiverse claim to it, and because its usefulness didn't depend on interpreting quantum mechanics any particular way at all. Willow's own name, incidentally, comes from Willow Glen, the San Jose neighborhood near Google's quantum hardware lab, continuing a company tradition of naming its quantum chips after places, following Sycamore and the earlier bristlecone processor, itself named for a species of ancient pine tree. It's a small detail, but the naming pattern reflects something true about how deliberately paced this program has actually been. Bristlecone in 2018, Sycamore in 2019, several unannounced intermediate iterations across the years in between, and finally Willow in 2024. Each one built specifically to attack the next unsolved technical bottleneck in the field, rather than to generate a headline on its own. The multiverse framing wound up being the loudest thing anyone remembered about Willow's launch, but it sat on top of a research program that had already been running, quietly, for the better part of a decade, before that one blog post sentence briefly became the entire story. None of this happened in a vacuum, either, and it's worth knowing Google wasn't the only company racing toward these milestones. Around the same period as Willow's debut, Microsoft announced its own quantum computing advance, a qubit virtualization system the company said had broken a record for creating reliable logical qubits, part of Microsoft's competing bet on a different underlying qubit technology. IBM, which had already sparred publicly with Google over the original 2019 Sycamore claim, has continued building out its own superconducting quantum roadmap in parallel, with its own error correction and scaling milestones on a similar multi-year timeline. That competitive backdrop matters for reading the Willow story correctly. Multiple well-funded, technically serious organizations, not just Google, are independently converging on similar below-threshold error correction results, using different hardware approaches and different underlying physics, which is generally a strong sign that a real physical phenomenon is being measured and replicated across the field rather than an artifact specific to one company's marketing or one company's choice of benchmark. By 2026, the pace kept accelerating. In March, Google expanded its hardware lineup beyond superconducting qubits, the technology behind both Sycamore and Willow, by adding a second complementary approach built on neutral atoms, individual atoms suspended and controlled with precisely tuned lasers rather than etched into a superconducting circuit and cooled to near absolute zero. It's a fundamentally different way of building a qubit, one that some researchers believe may scale to far larger qubit counts more easily than superconducting hardware, because neutral atom arrays can, in principle, be rearranged and reconfigured optically rather than requiring each qubit's physical wiring to be fixed at fabrication time. Google framed the move explicitly as running two complementary hardware bets in parallel rather than abandoning superconducting qubits, aiming to let whichever technology scales faster carry more of the weight toward a genuinely large, fault-tolerant machine. And in June 2026, at the ISE High Performance Conference in Hamburg, one of the longest-running and most attended events in the high-performance computing calendar, Google presented results claiming Willow had achieved a further quantum advantage on a different benchmark, again citing a roughly 13,000 times speedup over classical supercomputing hardware, this time framed explicitly around real scientific and industrial applications rather than an artificial stress test, and presented alongside competing announcements from China's National Supercomputing Center and other major players in the same conference week, underscoring just how quickly the entire field, not just Google, is now moving. None of these later results carried the same borrowed from parallel universes framing that made the original Willow launch a viral story, which is itself worth noting. Google's own scientists appear to have moved past leaning on the multiverse framing in every subsequent announcement, letting the verifiable application-oriented results speak for themselves instead. It's worth spending a moment on why researchers outside Google care about this progress at all, beyond the multiverse debate, because the eventual payoff, if the engineering keeps compounding the way Willow and quantum echoes suggest it might, is genuinely large and well-grounded in existing physics rather than speculative hype. A fully fault-tolerant quantum computer, the kind these below-threshold results are aimed at eventually enabling, would be extraordinarily good at one particular category of problem, simulating other quantum systems, because it is itself a quantum system, rather than a classical machine straining to approximate one. That category includes the exact chemistry quantum echoes was aimed at, molecular structure and reaction behavior, which matters enormously for drug discovery, since much of the cost and delay in developing new medicines comes from expensively simulating or physically testing how candidate molecules will actually behave and bind inside the body. It extends to materials science, where researchers have long wanted to simulate, rather than blindly search for, new battery chemistries, superconductors, and industrial catalysts, including a much-discussed long-term goal of finding a more energy-efficient catalyst for nitrogen fixation, the chemical process behind synthetic fertilizer production that currently consumes an estimated 1 to 2% of all global energy output. None of that is available yet, and Google's own team has been careful in public statements not to promise a specific timeline for reaching that fully fault-tolerant scale. But the below-threshold result is precisely the kind of foundational, unglamorous engineering milestone that has to be crossed before any of those applications become possible at all, which is a large part of why the physics and chemistry communities treated Willow's error correction achievement as significant independent of anything Neven said about parallel universes, because it's the kind of claim that sounds plausible if you don't know the underlying physics. And debunking it honestly is part of getting this story right, rather than part of hyping it further. In the days after Google's December 2024 announcement, some online commentary suggested Willow's speed meant it could break the encryption-protecting bank accounts, cryptocurrency wallets, and internet security broadly, essentially overnight. That claim doesn't hold up. Breaking widely used encryption standards like RSA or SHA-256 with a quantum computer requires running a completely different class of algorithm. Most famously, one developed by mathematician Peter Shor in 1994 on a fully error-corrected quantum computer with what researchers estimate would need to be millions of stable, logical qubits sustained over long, complex calculations, executing billions of individual quantum operations in sequence without a single uncorrected error breaking the chain. Willow, even with its below-threshold error correction breakthrough, operates with a small number of physical qubits assembled into a handful of logical qubits, nowhere near the scale cryptography breaking would require, and random circuit sampling, the benchmark that generated the 10 septillion year figure, is structurally a completely different kind of calculation from Shor's algorithm, one that happens to be extremely hard for classical computers to simulate, but has no bearing on factoring the large numbers that encryption keys are built from. Google's own team has been explicit about this gap in public statements, describing the distance to a cryptographically relevant quantum computer as still requiring orders of magnitude improvements across millions of components that don't yet exist. That gap is real, it's large, and it's a big part of why national cybersecurity agencies, including the U.S. National Institute of Standards and Technology, are already recommending organizations begin transitioning to newly standardized post-quantum encryption algorithms over the coming decade as a precaution well ahead of the actual threat, rather than because Willow itself poses any current risk. Separately, researchers in China have published work demonstrating limited attacks against reduced, non-standard versions of certain encryption schemes using quantum annealing hardware, a different technology from Google's gate-based approach, and those results, while genuinely worth taking seriously by security researchers as an early warning sign, are also a long way from breaking real-world encryption as it's actually deployed today across banking, government, and internet infrastructure. So where does that leave the actual defensible version of Google's quantum AI just broke physics? Not in the sense of disproving established physics or definitively proving the multiverse, which is not something a 5-minute benchmark, however dramatic the numbers, was ever capable of doing on its own, and no serious physicist on either side of the debate has claimed otherwise. What Willow and the quantum echoes result that followed it actually did was close in on a fundamentally different kind of milestone. A below-threshold demonstration that quantum error correction, the single biggest engineering obstacle standing between today's fragile, error-prone quantum chips and a genuinely fault-tolerant quantum computer, is not just theoretically possible, but achievable in a real physical device, and a verified, independently checkable speedup on a real scientific calculation less than a year later, confirmed against an actual measured molecule rather than only against another simulation. Those are the results that will matter in a decade, regardless of how the multiverse debate eventually settles, and they're the results other major labs, from IBM to Microsoft to teams in China, are independently racing to match or exceed using their own competing hardware, which is itself a sign the underlying physics is solid rather than an artifact of one company's framing. The parallel universe's framing, coming from a legitimate physicist, citing a legitimate decades-old interpretation of quantum mechanics that plenty of serious researchers still hold, wasn't empty marketing invented from nothing. But it also wasn't something Willow's specific benchmark could establish, and the physics community said so immediately in public under their own names, exactly the way a healthy scientific disagreement is supposed to unfold. What actually makes this story worth telling isn't a chip proving we live inside a multiverse. It's that a real engineering team spent nearly a decade chasing a threshold the field had pursued for 30 years, hit it, then followed up less than a year later with a second result that turned the achievement into something with a genuine application in chemistry, verified against a real molecule in a real lab, and then followed that with a broader hardware bet, adding an entirely second qubit technology to its roadmap within 18 months, betting that more than one physical approach might be needed to reach the eventual goal. Along the way, one of the field's own leaders made an interpretive leap that most of his peers thought went too far, said so plainly in a public blog post under his own name, and the disagreement got worked out in public, in blog posts and interviews and peer-reviewed rebuttals, rather than quietly, behind closed doors, the way institutional science sometimes gets accused of operating. That's not a broken universe, and it's not proof of one either. It's a genuinely hard engineering problem getting solved in full view of the public, followed by an honest, ongoing argument about what the result does and doesn't mean, which is a far better story and a far more durable one than either the multiverse headline or the encryption apocalypse rumor that briefly overshadowed it in the same news cycle.